So our next speaker is Huib, which you didn't meet him, please. He's an employee in Jive in Leiden and also an astronomy professor in Leiden. And if you've been paying attention, he's also the director of the Event Horizon Telescope project that has given us the image of the black hole. So let's give him an applause.
No need to give me a big applause because Tom apparently knows better than Tom. Okay, this is part 2, and we're going to interpret the image of the Galactic Centre black hole. So Violette gave you all the background information and introduced the M87 image that we published in 2019, and now we're going to zoom in on the Galactic Centre. And that's much closer because that's our own black hole, or at least our own supermassive black hole. We live in the Milky Way, a spiral galaxy, that, as far as we can tell, and we are some 27,000 light years away from its center. And we have reason to believe that at the center of every galaxy there is a supermassive black hole of some sort. Here's a picture of one of my colleagues in Drenthe. As I was introduced, I work for Jive most days, and I'm desperate for getting back to Drenthe tomorrow without a train ride. So let's zoom in on the Galactic Centre, 27,000 light years away in the constellation of Sagittarius. So it's a summer constellation, so it's very difficult to see here. It's low on the horizon. If we zoom into the Galactic Centre, we will have to switch from visible light to infrared light because of all the dust in between. We switch to infrared light, and we actually really don't know from this picture where the Galactic Centre is, but from radio images we know that the center must be in this direction, in Sagittarius, and we zoom in further and further, and you see that there is a very dense stellar cluster at the Galactic Centre, and when we follow that cluster of stars with an infrared telescope, the largest infrared telescopes we have, we can actually see the stars move on the sky. And if stars move on the sky, it must mean that they go very, very fast, because usually we cannot see even over a couple of years to see stars make any motion. And this is because the stars that we just zoomed in on are in orbit around the supermassive black hole at the Galactic Centre, our supermassive. And we've known this for a couple of years, and my colleagues Reinhard Genzel and Andrea Gates received last year's Nobel Prize for that. No, that's already 2 years ago. Because by measuring the orbits of these stars with infrared telescopes, they have deduced that there must be a 4 million solar mass equivalent black hole right at the center of our galaxy. And because that gravity attracts the stars nearby, the stars speed around that black hole. And that's very interesting because compared to the M87 galaxy that's far, far, far away, here we have a black hole that we can measure the mass and the distance of very precisely. Because we see these stars move around and also in our line of sight, we can measure very accurately the distance and also the mass of the attractor at the center. So we can now zoom in also with our radio telescopes, and the radio sky looks quite different. It's not dominated by stars, but it's dominated by the hot gas that's in between the stars. And hopefully we now go zoom in. Oh, we also have dramatic music here. And the Galactic Centre is really special in radio. There's no question when you look with radio eyes where the center of the galaxy is. There's all these spurs indicating magnetic fields, and then there is this spirally structure in the middle, and and there is a very bright central source to that spiral. And that source, when we resolve it further and further, is the image of the supermassive black hole at the Galactic Centre. And when I was at ESO, I had to build up the tension for that moment. But here I really want to try to explain to you what you're looking at. So to make this image is really complicated, and we have already seen this in the quiz. So 1/3 of you already knows this. The real difficulty of measuring the Galactic Centre black hole is because that it's very variable. These are two simulations of a few million solar mass black hole on the right and a several billion solar mass black hole on the left. And if you look very carefully, you see the left image change slightly, but on the same time scale, the Galactic Centre black hole is just looping around like crazy. Stuff goes around that black hole in a few minutes rather than a few days. Okay, so that makes it very difficult for us to image it. Violette has explained how we can deduce the image of something very small on the sky that feel the eye, but then you really have to have a source that stays stable while the Earth rotates and builds up all these baselines. So this is why it took us 3 years extra to make the image of the Galactic Centre black hole, even if it's more fundamental to us than the black hole in '87. And it's more fundamental because we know here how distant and how massive it is. So we had to do thousands and thousands of calculations trying to deduce an average image. And every image we did with slightly different parameter settings and calibration factors. And this is the average image we show to the world. To our colleagues, we do it slightly more careful. We put all these images in different families of images. And in our paper, we produce these 4 images that look similar but not the same. And we give a relative likelihood of all these images to be true. And so you see 3 of them have ring structures, the different azimuthal structure around it, and the 4th doesn't really look like a ring. And I have to be honest and say that all of these images are consistent with the data that we took in 2017. We have convinced ourselves that the artifacts that you see in these images are due to the fact that the source varies, and we are very confident that we have a ring. Oh, yes, so this is the image we show in the scientific publications. And so, where in M87 we knew that a 42 microarc second image, 42 microarc second diameter image was consistent with a 6.5 billion solar mass black hole at 54 million light years. We now have a much closer, 1,000 times closer black hole, which is 1,000 times lighter. And we have a very happy coincidence that we live on a planet where we can get a resolution of about 10 microarc seconds, and we have 2 black holes on the sky that look very similar, although one is 1,000 times further away. So this is when you put them to scale. Okay, now the thing that is the most difficult to explain, and which the general public probably does not get, in fact some of my colleagues don't get, is what are you actually looking at? And this was a question that Violette got after her talk, and so I will try to explain. So in general, radio emission comes from very, very hot plasma, so very hot electrons that float in interstellar space and which are accelerated in magnetic fields. And this will happen around black holes. But black holes do something special to this, because black holes have such a strong gravity field that it will bend the light that comes from its surroundings. And so light from all kinds of directions around the black hole is being mapped to our line of sight. And it looks the same for observing in a different direction, but we're just concentrating on an observer towards the right side of the image. In fact, some light will go around the black hole more than once, and you get an image. You get a zeroth order image of gas radiating, and you get the first order image of of gas that radiates and goes around the black hole, and a second and third and fourth order. So the image that you see is not looking like a donut because we're looking into a donut. It looks like a donut because the black hole in our line of sight is lensing, is imaging the emission from the hot gas around it. And if you could make a picture this good, we could actually test Einstein's theory in great detail, because we could discern the different orders of emission and measure very accurately whether Einstein is right. But in reality, we are blurring this with the resolution of our telescope. We have a very, very, very impressive telescope that is as big as the whole planet, with atomic clocks and digital equipment. But the most important thing still is that our image of that black hole is limited to that resolution. We cannot see greater detail, finer detail than that. Then I've drawn on this 3 rings, and the white one was that was question 10, I think, in your quiz. The white one is the Schwarzschild radius. That's the projected size of the event horizon itself. If you go beyond that, nothing can ever come back to the rest of the universe. The blue one is where we expect the photon ring to be imaged, which means the gravitational band light. And the purple line is where stuff can still do an orbit around the black hole. So to actually test Einstein's gravity, we have to disentangle these different mechanisms to make an image. And we're going to do that with simulations. And in the simulations, a few things are important. A black hole can have a different mass. It can be heavy or light. And for the Galactic Centre, that's easy because we know exactly from the stellar orbits what it's supposed to be. A black hole can have spin. It can have angular momentum and drag its surroundings around. So we have to model different spins. Oops, I should yeah, that was a mistake. And I think there's no other way than to sit through the whole movie again. Maybe a good time to take a sip of your beer. So this is the rotation of the black hole, and then the next parameter is that we also have to assume an inclination for the black hole. And this is the only part where Sagittarius A star in our galaxy is worse than M87. In M87 we see a very bright jet, and that means we know how the black hole is oriented with respect to the sky, as in this simulation. But for the Galactic Centre black hole, we haven't found a jet, or there is no jet, possibly because we're starving. The black hole in the Galactic Centre is starving, and therefore we don't have a priori knowledge about the inclination. And the inclination is important. It's a bit like the image in the movie, because if you see the black hole edge on, it has to be brighter on one side because of its rotation than the other. And if you see a black hole which is symmetric, it must mean we are looking at it more face on. So these are ingredients to our simulations, but there are many more ingredients to our simulations. The temperature of the gas in orbit around the black hole, whether it's electrons or positrons that are being accelerated. A lot of details are going into enormously large and complex calculations. And then we can rule out some of these models because of our observations and constrain that way what we think the Galactic Centre black hole is like. And so what's left over here are our best ideas of what the Galactic Centre black hole, how we make it look, how it comes to look like it does. So, that's exactly what was in the quiz. We think that because the Galactic Centre black hole looks so smooth, we must be looking at it face on. I think Violette already covered most of these future outlooks. This was only the 2017 data, so you can expect much more detailed observations from 2018. We skipped 2019, 2020, there was Corona. 2021, we have also good data. 2022, we have data. And we are improving our telescope every year. And these are actually the same conclusions here that I use when I give a scientific talk. So what we have demonstrated with these observations is that we get the ring that Einstein's general relativity predicts. The difficult but strong message is that such a star is for us a much more fundamental result because we measure something where we have good constraints on the distance and mass. And a bit to our surprise, it seems to be that we are looking at a black hole down its rotation axis, which is a bit strange if you consider that the rest of the galaxy is, of course, edge on from our perspective. And we haven't seen it yet, and that must mean it has very low accretion. This was normally my last slide, but I would like to take the opportunity here to advertise this year's fourth lecture, which is given by one of the founding fathers of the VLBI technique, Professor James Moran from Center of Astrophysics in Harvard. And there should be announcements all over the web or in your local library, and I think there's still a few seats left if you make your reservation. Thank you. Questions? Yes?
So what you see here is actually not the accretion disk, but it is more light coming from other sources that is focused by the black hole.
Yes. So in the case of Sagittarius A star, we think that maybe the accretion is not very strong at all, and it just lives in a maybe even a quite filled spherical bubble of plasma, and it gets to be imaged into a ring because of the gravitational field.
And we need to look at it head-on, more or less.
Yeah, well, that's a very, I should posit, that's a preliminary result of our interpretation, that we think that most of these black holes should have considerable rotation, and the rotation axis, quite surprisingly for this one, seems then to point towards us.
Does it also mean that if there were a yes, it would also come direct to us?
Yes. But for instance, all our models at the moment assume that the rotation of gas and the rotation of the black hole are always in the same direction. So there could be ways out in more complicated models, but yes.
One of the main problems is the dynamics of the system. And still we get a still picture of our black hole environment.
Yeah.
What can we say, what could we expect from understanding of the dynamics of the system?
Yeah, okay, so I have not talked much about that. So in this talk I have only given you an average image, our best average image. We've also tried to see if we can make time slices and see whether you can put any of these uncertainties in the motion. At the moment we don't have enough data to do that. It's certainly our hope that in a couple of years we could make a movie where you could see the variations actually take shape. One intriguing result is that at the moment our models actually give more variability than what we see on the sky. So there's also some physics there that we not completely understand yet. Just to give you an idea of how uncertain, how early these results
are. You see, how is it possible that that light sometimes goes twice around the black hole, and then can you see this in this picture that there's a second image or something from the same thing, or is it?
Yeah. Okay. So to explain this, it's better to think of photons the other way around, right? And we were standing here 27,000 light years away from the Galactic Centre, and we see only the photons that come directly into our line of sight from the black hole. And these can be photons from stuff several radii away that comes directly to us, or it can be stuff coming from the background with a certain impact parameter that is dense towards us, or it can be stuff that's maybe close to the black hole but happens to have an impact length that it goes around several times before it gets to us. It's just a very complicated imaging of the surrounding of the black hole into our line of sight.
But you see this in the picture you showed that there's actually it's double, sometimes the same from the same source.
Yes.
Yeah.
Yeah. And so if you have infinitely good resolution, you should be able to distinguish the radius of the stuff that has gone around once or twice or 3 times, but then you have to have extremely good resolution, and even with the space field application, we could hardly ever distinguish that.
If we assume for a moment that the black hole is, if something were to fall in and it would produce a jet, and we were directly in the path of that jet, what would happen here? Would we see anything? Would it be cataclysmic?
Yeah, I think you get a very spectacular version of the Northern Lights, probably. No, but I don't want to scare anybody. I usually get questions when are we going to fall into the black hole? No. No. I mean, it's a fantastic thing on astronomical scale, right? But the density, even the density of the space quite close to the black hole is still much less than the density of matter on our planet, right? It's still very, very vacuum-like. It has high energy, but it is not very dense, so it doesn't carry enough energy to do any harm. We can see the radio light, and sometimes the real light, but it's still very low density stuff.
Are there any other targets considered, or are these 2 candidates basically the ones
Yeah. So unfortunately, it seems that these are really the only two targets that we can get with current instrument. I think the next best thing is SEM-A, of which Centaurus A, of which Violette showed an image. I think it has 5 times less smaller ring on the sky. So we would have to have a telescope 5 Earth diameters away to see that. In fact, you could turn it around. We'd be very lucky that we are on a planet just big enough to see these.
There's talk of like building a radio telescope on the moon, something like that.
Yeah, that would be great.
Or two. One question about, we see light from the environment of our black hole. What does it tell us about the degree of activity around it?
Yeah, so in these models, the accretion rate of the black hole is a parameter, and this black hole, I think, our Galactic Centre black hole, I think, if I remember correctly, it's less than 3 moons a year, and that sounds like a lot, but for a black hole, that's really very local. Okay, last question.
For the future, so what I understood is there will be more telescopes. That is to enhance the sensitivity, but you cannot really enhance the resolution, is it? Or
No, but okay. So the most important thing why we want more telescopes is it now takes us about an observation run of 4 hours to get some sort of. You saw the way the image is made up of these combinations of telescopes. So if you have 2 times more telescopes, you get 4 times more combinations, and so that would give us a much faster imaging capability. So we could see things actually move and make an image if we had more telescopes. Okay, Pierre.